Weightage for GATE is 7 to 9 marks every year. For ESE, it is 12 to 20 marks in prelims and 5 to 70 marks in conventional, ESE conventional. Okay, syllabus will go in this order only: fluid properties, fluid statics, fluid kinematics, fluid dynamics, internal flows, laminar flow, turbulent flow, flow through pipes, external flows, boundary layer, lift and drag forces, dimensional analysis, hydraulic machines. This star indicates importance, like how many times it is repeated in GATE exam. If you want, these are reference books. Fluid. Fluid is a substance which deforms continuously under the action of shear stress. In simple words, anything that can flow can be considered as fluids. Example: all liquids and gases. Solid doesn't deform continuously under action of shear stress. Fluid deforms continuously under action of shear stress. So difference between solid and fluid. Solid may regain original shape after removal of shear stress. For fluid, deformation is permanent. For solid, tau directly proportional to pi within elastic limit. Shear strain is directly proportional to shear strain. Hooke's law. For fluid deformation, in fluid, absolute value of shear strain is not important, but rate of shear strain is important. Tau directly proportional to d pi by dt, or du by dy, Newton's law of viscosity. Continuum hypothesis: fluid is assumed to be continuous substance without any empty space or voids. But in actual reality, it will be like this: dots are molecules. The assumption is that there are no empty spaces. Continuum hypothesis simplifies the analysis of fluid flow because molecular approach is not required. It also allows use of calculus in study of fluid flow. Continuum hypothesis will not be valid if intermolecular spacing becomes comparable with the size of object with which fluid is interacting. In such cases, laws of fluid mechanics are not valid. To check validity of continuum hypothesis, a dimensionless number called Knudsen number is used. It is defined as Kn is equal to lambda by L, lambda mean free path, average distance between two successive collisions, L characteristic length of object. For validity of continuum hypothesis, Kn less than 0.01. Chapter 1: Fluid Properties. Contents: basic properties, density, specific gravity, specific weight, bulk modulus, compressibility, coefficient of volumetric expansion, viscosity, kinematic viscosity, surface tension, angle of contact, vapor pressure. Density is equal to mass by volume. Rho water is equal to 1000 kg per meter cube at 4 degrees centigrade. Rho is equal to m by v. Water has unique property, like density is maximum at 4 degrees centigrade, that is 1000 kg per meter cube. It varies with temperature, like this density. Rho mercury is equal to 13,600 kg per meter cube at 10 tp. P air is equal to 1.17 at 10 tp. For any other temperature or pressure, PV is equal to MRT, rho is equal to P by RT, R is equal to 0.287 kilojoule per meter cube. This is for air. Kilojoule per kg per Kelvin. Specific gravity or relative density. Specific gravity is equal to rho substance by rho reference. Unit to unitless dimension m power 0, l power 0, t power 0. Rho reference is equal to rho water for solid or liquid substance. Rho reference is equal to rho air for gaseous substance. Specific weight, W or gamma. Specific weight is equal to weight by volume. W or gamma is equal to mg by v is equal to rho g. Unit Newton per meter cube. Dimension m l power minus 2 t power minus 2. Bulk modulus K. K is equal to volumetric stress by volumetric strain. Unit Newton per meter square. Dimension m l power minus 1 t power minus 2. K is equal to minus dp by dv by v at t is equal to constant. K is equal to minus v dp by dv at constant temperature. Bulk modulus consists of effect of pressure on volume or density of the fluid at constant temperature. It is defined as ratio of volumetric stress and volumetric strain. Rho is equal to m by v and rho v is equal to m. d of rho v is equal to dm. dm is equal to 0. d rho by rho is equal to minus dv by v. So k is equal to minus dp by d rho minus dp by minus d rho by rho. Minus cancel at t is equal to constant. K is equal to rho dp by d rho at constant temperature. Bulk modulus of a substance indicates how easy or difficult is that substance to compress. High value of K indicates that high pressure change is required for a given volumetric change, that is, the substance is difficult to compress. Compressibility alpha. Alpha is equal to 1 by K, unit meter square per Newton, dimension m power minus 1, L power 1, T power 2. Compressibility is defined as reciprocal of bulk modulus. High value of compressibility indicates that the fluid is easily compressible. Hence, it is called compressibility. Alpha is equal to minus of dV by V by dP at T is equal to constant. Alpha is equal to minus 1 by V dV by dP at constant T. Alpha is equal to 1 by rho d rho by dou P. Dou rho by rho P at constant temperature. Coefficient of volumetric expansion beta. This considers effect of temperature on volume or density of fluid at constant pressure. It is analogous to coefficient of thermal expansion of solid. The change in volume due to temperature is directly proportional to change in temperature and original volume. The constant of proportionality is called coefficient of volumetric expansion. dV directly proportional to dt and directly proportional to V. dV is equal to beta V dt at pressure is equal to constant. Beta is equal to 1 by V dou V by dou T at constant pressure. Beta is equal to minus 1 by rho dou rho by dou T at P. Unit 1 by Kelvin, dimension m power 0, L power 0, T power 0, theta power minus 1. Note, if temperature and pressure both are changing, then total change in volume can be obtained by adding change in volume due to pressure change alone and change in volume due to temperature change alone. V is equal to V function of P comma T. dV is equal to dou V by dou P into dP plus dou V by dou T into dt. dV is equal to minus alpha V dP plus beta V dt. This is minus alpha V dP is change in volume due to pressure change. Beta V dt is change in volume due to temperature change. dV by V is equal to minus alpha dP plus beta dt is equal to minus dou rho by rho. Minus dou rho by rho. Okay. This is one previous paper question. Simple one. A pressure vessel of volume 0.5 meter cube needs to be tested for pressure of 300 bar by pumping water into it. At 300 bar, the pressure vessel expands by 6%. The mass of water in kilogram needs to be pumped into pressure is. So, here dV by V is 6%. 0.06. So dV by V is 0.06. V1 is 0.5. V2 is 1.06 into 0.5. At important fact thing is at 300 bar low water will not be equal to 1000. So we should not use directly 1000. K is equal to dP by d rho by rho. D rho F is equal to rho I plus d rho. K is given. K is given. M of final is equal to rho final into V final. So we can finally get it as 538 kg. That is mass of water is asked in kilogram. Okay. Quotient of volume expansion of ideal gas is given by beta is equal to dou V by dou T into 1 by V. PV is equal to MRT. We can write dV by dt, MR by P. Finally, beta is equal to 1 by T. For ideal gas, show that isothermal compressibility is given by alpha is equal to 1 by P. Alpha is equal to minus dou V by dou P into 1 by V. PV is equal to, again PV is equal to MRT. P dou V plus VdP is equal to 0. From that, dV by dou P is equal to minus V by P. Finally, alpha is equal to 1 by P. Viscosity mu. This bottom plate is at rest, U is equal to 0, but top plate is moving with U velocity. Fluid is flowing in between. Then fixed plate, moving plate. V is equal to U. Viscosity represents friction within the fluid. Thick fluids have high viscosity compared to thin fluids. At interface of solid and fluid, no slip condition exists. That is, relative velocity between solid and fluid layer in contact with solid is 0. Between two adjacent fluid layers, slip is permitted. Velocity gradient, it is the rate of change of velocity with respect to normal direction to the flow velocity. dy u, u plus dy, u plus du. Velocity gradient du by dy. Velocity gradient also represents slope of a tangent to the velocity profile measured with respect to normal direction of flow velocity. Du by dy is equal to tan theta. This is moving with u, and d at a distance dy, it is moving with the fluid element is moving with u plus du. This angle is theta. Tan theta is equal to, this is du, this is dy. Tan theta is equal to du by dy. Newton's law of viscosity. The shear stress between two adjacent fluid layers is directly proportional to velocity gradient or rate of shear strain. Tau directly proportional to du by dy or d pi by dt. Tau is equal to mu du by dy. U plus du, tau in this direction, in this direction. D pi is equal to tan of d pi. Let's consider fluid element A, B, C, D. It is deformed by like this. D pi, tan A pi is equal to tan of D pi is equal to BB dash minus A dash by AB. D pi is equal to U plus DU into DT minus U DT by DY. D pi is equal to DU DT by DY. D pi by DT is equal to DU by DY. Tau directly proportional to du by dy. Tau directly proportional to d pi by dt. Viscosity mu is equal to tau by du by dy. Unit of mu is equal to Newton second per meter square is equal to kg per meter second is equal to Pascal into second. Dimension of mu is equal to m power 1 L power minus 2 T power minus 1. CGS unit Poise is equal to gram per centimeter second. 1 Poise is equal to 1 by 10 kg per meter second. 1 Pascal second is equal to 10 Poise. If 10 Poise, if velocity, if velocity profile is linear, then du by dy can be written as delta u by delta y. Delta u by delta y is equal to du by dy if it is linear like this. Okay. One question from previous paper, as gap is small, velocity variance can be assumed to be linear. From that, tau is equal to mu delta u by delta y. From FBD, block driving force and resisting shear force must be same. It can be shown that velocity profile is linear if pressure gradient in the direction of flow is 0. In the direction of flow is 0, irrespective of distance between surfaces. Pressure in the direction of pressure gradient in the direction of flow is 0. Okay, one more question. Okay, is equal to, when the block is released, final velocity is called terminal velocity. The question is asked about terminal velocity. Again, these are normal questions. Okay, velocity of u profile is given, du by dy we have to get from this, and mu distance from surface, where shear stress value is half of shear stress at surface. Okay, surface means at y is equal to h. At a surface means y is equal to, okay, y is equal to 0. Y is equal to h, and then I can get at what y. Mu h1 h2. Determine velocity at interface. It may be moving with v and linear profile is given. Mu du by dy is equal to at interface tau top tau bottom at interface it should be equal. So 0.15 into 1 minus vi by 0.3 is tau vt top at as linear profile. The shear stress is constant throughout the two fluids. Equate shear stress. At interface, shear stress are equal. Hence, shear stress at any point between 2 points is constant. Okay, circular disc are kept on flat surface. The fluid of viscosity mu and angular velocity omega, magnitude of resisting torque on the disc due to viscosity. Assume velocity. Okay. Due to circular motion, velocity at different point on the disk varies linearly with respect to radius. The variation in velocity leads to variable velocity gradient and shear stress. Okay, the resisting torque tau is equal to mu du by dy is equal to r omega by h. R omega h at distance dr. Tau is equal to mu into r omega by h. The torque is tau into dA. dA is 2 pi r dr into r is distance. So torque is to be found at integral dt. Then we will get 2 pi omega r power 4 by 4 if we integrate from 0 to r, pi omega r power 4 by 2h. If it is like this at theta, then pi mu omega r power 4 by 2h sine theta. Everything is same, but sine theta is there. If it is like conical and the flat surface, then t is equal to 2 pi mu omega r cube by 3 theta. Like we have to do integration for everything. Effect of temperature on viscosity. In liquids, viscosity is present due to intermolecular cohesive forces of attraction. Temperature increases, intermolecular spaces increases, the cohesive forces of attraction decreases, and hence viscosity of liquid decreases with respect to temperature. In gas, intermolecular spacing is very high as compared to liquid, hence cohesive forces are negligible. In gas, viscosity is present due to momentum exchange between two adjacent layers. One molecule from a slower layer jumps into faster layer, then it exerts a retarding force on faster and vice versa. As temperature increases, molecular activity increases, intermolecular moment exchange rate increases, hence viscosity of gas increases. Mu temperature for gases it will increase, for liquids it will decrease. Mu is equal to a e power b by t. For liquids, mu directly proportional to root t. For ideal gas, mu directly proportional to t power n. For real gas, n is equal to 0.5 to 0.7. Kinematic viscosity V. Kinematic viscosity is defined as ratio of dynamic viscosity and density of fluid. V is equal to mu by rho. Mu is equal to dynamic or absolute viscosity. Rho is equal to density of fluid. Unit of kinematic viscosity meter square per second is similar to the unit of kinematic quantities like velocity, acceleration. Hence, it is called kinematic viscosity. Kinematic viscosity is also called momentum diffusivity because higher the kinematic viscosity, faster is transfer of momentum within the fluid. Delta directly proportional to root V. Delta root V. Unit of V meter square per second. SI unit dimension m power 0 L square t power minus 1. CGS unit stroke. 1 stroke is equal to 1 centimeter square per second. 1 meter square per second is equal to 1 into 10 power 4 centimeter square per second. 1 meter square per second is equal to 1 into 10 power 4 strokes. Water is heated from 25 degrees to 120 degrees at atmospheric pressure. Which of the following gas represents correct variation of viscosity? Viscosity with respect to temperature. First decreases as it is liquid at 100 degrees phase change. So there will be a sharp decrease, and then gas increases. Velocity of liquid decreases with respect to temperature, and for gas it increases with respect to temperature. The viscosity of saturated water is more than that of saturated vapor. V of air at 20 degrees is 1.6 into 10 power minus 5 meter square per second. The approximate value of at 70 degrees centigrade will be V is equal to mu by rho, V directly proportional to T root T, V directly proportional to T power 3 by 2. From that we can get it is equal to 2.02. Near that value we can put answer. Non-Newtonian fluids. Fluids which do not follow Newton's law of viscosity are called non-Newtonian fluids. Non-Newtonian fluid, time-independent, time-dependent. Time-independent, Bingham plastic, pseudoplastic, dilatant. Pseudoplastic is also called shear thinning. Dilatant is also called shear thickening. Time-dependent, thixotropic, rheopectic. The classification of non-Newtonian fluids is based on apparent viscosity. Apparent viscosity, it is defined as ratio of shear stress and shear strain rate or velocity gradient. For Newtonian fluid, this ratio is constant, whereas for non-Newtonian fluid, this ratio is not constant, hence it is called apparent viscosity. Physical significance of apparent viscosity is same as dynamic viscosity of Newtonian fluid. Bingham plastic fluids have dual nature. If applied shear stress is small, they behave like solids. But if shear stress exceeds certain minimum yield stress, then they behave like solids. D pi by dt is equal to 0, mu is equal to tau d pi by dt tends to infinity. And this is Newtonian fluid slope mu. This is ideal fluid which is tau is equal to 0. This tau increases, and then it will have straight line, that is Bingham plastic. This is solids. Pseudoplastics shear thinning. If apparent viscosity of non-Newtonian fluid decreases with respect to shear stress or shear strain rate, then fluid is called pseudoplastic or shear thinning. Tau graph du by dy, theta 1 greater than theta 2, mu a1 greater than mu a2, mu a is decreasing. Mu a1 tau 1 by du by dy 1 tan theta 1, mu 2 a2 tau 2 by dau by dy tan theta 2, theta 1 greater than theta 2, mu a1 greater than mu a2, mu a1 greater than mu a2. Shear stress, this pseudoplastic or shear thinning, mu a1 greater than mu a2, so mu a is decreasing, that is why shear thinning. Dilatant shear thickening. If apparent viscosity of non-Newtonian fluid increases with respect to applied shear stress or shear strain rate, then a fluid is called dilatant fluid. Tau du by dy theta 1 theta 2, dilatant mu a1 is equal to tau 1 by du by dy 1 is equal to tan theta 1, mu a2 is equal to tau 2 by du by dy 2 is equal to tan theta 2. Theta 2 greater than theta 1, mu a2 greater than mu a1. Power law for time independent fluid, tau is equal to a du by dy whole power n plus b. Bingham plastic, n is equal to 1, b not equal to 0, b is equal to tau naught. Pseudoplastic, n less than 1, b is equal to 0. Dilatant plastic, n greater than 1, b is equal to n greater than 1, b is equal to 0. Dilatant is shear thickening, n greater than 1, mu a increases. Okay. For dilatant and pseudoplastic, B is equal to 0, tau is equal to A du by dy whole power n, mu A is equal to tau by du by dy is equal to A du by dy whole power n minus 1. For pseudoplastic, as du by dy increases, mu A decreases, n minus 1 less than 0, n less than 1. For dilatant plastic, as du by dy increases, mu A increases, n minus 1 greater than 0, so n greater than 1. Thixotropic, if apparent velocity of non-Newtonian fluid decreases with respect to time even though applied stress or a velocity gradient is constant, then fluid is called thixotropic fluid. Rheopectic fluid, if apparent viscosity of a fluid increases with respect to time when either shear stress or velocity gradient is kept constant, then it is called rheopectic. Mu a time, Newtonian time independent, non-Newtonian. Thixotropic or rheopectic. Thixotropic, it decreases with respect to time. Rheopectic increases with respect to time. Surface tension, free surface of liquid behaves similar to the stretched elastic rubber surface. It always tries to minimize its area as if it is under tension. The tensile force present inside the surface is constant and it is called surface tension. The direction of surface tension force is tangential to the surface and perpendicular to the line on which it is acting. If you consider this fluid element on surface, this F1 will be like this, F2 will be like this, F1, this length is L2, this length is L1, F1 by L1 is equal to F2 by L2. In free body diagram of surface, the surface tension force is shown only on the boundary because internal forces always gets cancelled. The surface tension effect is result of intermolecular forces. The liquid molecules which are well below the surface are attracted equally in all directions due to equal cohesive force exerted by adjacent liquid molecules. Such molecules do not experience any net force. On other hand, the liquid molecules which are on a surface are attracted by strong cohesive forces of liquid molecules and weak adhesive forces of air molecules towards the air. Since intermolecular spacing of air molecule is higher than liquids, cohesive force of liquid is higher. Therefore, molecule on a surface experiences net force towards liquid. The liquid tries to minimize the number of molecules on surface. This leads to area minimizing tendency of the surface and behaves like stretched elastic member. If we put water like this will have in all directions, it will be balanced, but on the surface there F it will be in this downward direction. It will be pulling. Surface energy F sigma into x and F sigma into y. Work done by external forces to stretch the surface of liquid is stored in the form of energy is called surface energy. The surface energy can be considered analogous to potential energy. The work required to increase area of rectangular surface of size x into y is given by dw is equal to sigma into x dy by 2 into 2 plus sigma y into dx by 2 into 2. Sigma is equal to x dy plus y dx. Sigma is equal to sigma into dxy. dw is equal to sigma dA. Sigma is equal to dw by dA. Surface energy per unit area is equal to the value of surface tension of for the liquid. Unit Newton per meter or joule per meter square. Dimension m t power minus 2. Sigma water is equal to 0.072 Newton per meter at room temperature. Angle of contact theta. These are forces. This is between liquid. This is between liquid and solid of this material. This is between solid and this is between liquid and gas. Okay, FL. This is acute. This is obtuse angle. Theta less than 90 degrees. It will be like this. Theta greater than 90 degrees. It will be like this. Angle of contact is defined as angle between solid surface and tangent to the liquid surface at point of contact. Angle of contact is always measured on liquid side. For example, this tangent and this solid surface on liquid side theta, this tangent and on this surface the angle theta. The angle of contact is result of intermolecular forces exerted by solid molecules, gas molecules, and liquid molecules on liquid molecule near to the point of contact. If force exerted by solid molecules are stronger as compared to liquid molecules, then liquid surface rises near the point of contact and angle of contact less than 90 degrees. On the other hand, if forces exerted by liquid molecules are stronger as compared to solid molecules, then liquid molecules depressed at point of contact and angle of contact is more than 90 degrees. And angle of contact is more than 90 degrees. Okay, this force is more, liquid's force is more. Angle of contact is not property of liquid alone, it strongly depends upon solid with which it is in contact. Angle of contact is also slightly affected by impurities present inside the liquid and the surface roughness of solid. Okay, then determine large diameter steel pin which can float on surface. Neglect effect of buoyancy, assume steel. Okay, sigma is given. Yes, sigma into L, sigma, and P is kept on surface. The surface gets depressed at point of contact. The vertical component of surface tension is responsible for balancing. As spin diameter is gradually increases, the value of theta decreases, and in limiting case it becomes 0. Sigma Fy is equal to 0. 2 sigma L into cos theta. If you put a pin, sigma will be in this direction and in this direction at an angle theta. 2 sigma L cos theta is equal to W. Here theta you can take it directly 0 and is equal to W. From that we can get D. Determine force required to lift metal ring from surface. Okay, metal ring. This here it is metal ring. Everywhere there will be sigma into pi d into cos sigma into pi d into 2 because there are inner and outer surface, f inner, f outer. F is equal to 2 pi d sigma. Okay, when ring is being lifted from surface of water, surface rises near the point of contact. The surface tension forces are tangential to water surface at point of contact. In limiting case, the water surface at point of contact will be vertical line. Hence, surface tension forces acting on ring are in downward direction, are downward. Liquid drop capillary broken into 8 small drops of equal size. What is work required during the process? Capital R cube is equal to 8 small r cube. R is equal to capital R by 2. dW is equal to sigma into dA. Sigma into dA. Initial minus final. 4 pi r square is initial. 8 into 4 pi r by 2 whole square is final. Final is equal to 4 pi sigma r square. If a drop is broken into small parts, the volume of liquid remains same, but surface area increases as more number of liquid molecules are exposed on the surface. The increase in surface area leads to increase in surface energy. The difference in surface energy must be supplied as external work. The difference in surface energy must be supplied as external work. Pressure rise in liquid jet due to surface tension. P in this is liquid jet. P in greater than P out. P out is just atmosphere. Liquid jet exposed to air. P in P out. Sigma L D sigma L in this direction. Sigma if we cut it into half. The free surface of jet tries to contract due to the surface tension. Hence pressure inside jet will increase. The increase in pressure can be determined by considering FBD of cylindrical jet surface, semi-cylindrical jet surface. The pressure difference on surface acts in radially outward direction. The horizontal component of pressure gets cancelled due to symmetry, and vertical component must be balanced with surface tension force. Sigma Fy is equal to 0. Delta P into AP. AP is projected area. Delta P into AP minus 2 sigma L is equal to 0. Delta P into D into L is equal to 2 sigma L. Delta P is equal to 2 sigma by D. Delta P is equal to P in minus P atmosphere. Pressure rise in liquid drop due to surface tension. P out is equal to P atmosphere, P in P atmosphere, sigma into pi d, delta P into pi by 4 d square, delta P into pi by 4 d square is equal to sigma into pi d, sigma into pi d, if we cut it into half, and delta P into pi by 4 d square is projected area. Delta P is equal to 4 sigma by d. So pressure rise in soap bubble due to surface area. Here, as it is bubble, there will be two surfaces. 2 sigma into pi d is equal to delta P into pi by 4 d square. Delta P is equal to 8 sigma by d. Delta P is equal to 2 sigma by d is equal to sigma by r for liquid jet. Delta P is equal to 4 sigma by d is equal to 2 sigma by r for liquid drop. Delta P is equal to 8 sigma by d is equal to 4 sigma by r for soap bubble. In general, pressure on concave side of surface is more than convex side. The difference in pressure is because of surface tension and is given by delta P is equal to sigma into 1 by r1 plus 1 by r2. Where r1 and r2 are principal radius of curvature. If this is like this, then theta 1 r1 r2 r1 r2. Okay. Capillary action. If you put a small diameter tube into water surface, then it will rise till a height h because of surface tension. Sigma into d, sigma pi d cos theta. Sigma pi d, then if theta is this angle, if we rotate it, then into vertical direction, sigma pi d cos theta, net resultant as horizontally will be balanced. PD is equal to PC is equal to P atmosphere. PB is equal to PC minus rho GH. PD PC as both P atmosphere. PB is equal to PC minus rho GH. When tube of narrow diameter is dipped inside liquid, then a meniscus is formed on inner side of tube due to angle of contact effect. The meniscus is at a level of free surface of liquid is unstable because it experiences unbalanced surface tension force in vertical direction. Therefore, meniscus travels in direction of net surface tension force until driving force is balanced by some resisting force. From FBD of liquid column in the tube, we get summation of Fy is equal to 0, sigma Fy is equal to 0, sigma into pi d into cos theta minus rho gv is equal to 0, sigma into pi d cos theta is equal to rho g into pi by 4 d square h is equal to 4 sigma cos theta by rho gd. Sometimes it will get depressed also at a height h. P atmosphere in the top is P atmosphere, bottom is P atmosphere plus rho gh. Bottom P atmosphere plus rho h, sigma into pi d cos theta, sigma F is equal to 0, delta P into AP is equal to sigma into pi d cos theta, rho g h into pi by 4 d square, sigma pi d cos theta, h is equal to 4 sigma cos theta by rho gd, we can say h is equal to minus 4 sigma cos theta by rho gd. Normal question only. Two parallel plates, then we can write sigma into L cos theta. If you wrote it, 2 sigma L cos theta is equal to rho g h into T into L. So h is equal to 2 sigma cos theta by rho g L. When the capillary tube is cut at certain height, weight required to balance reduces and it will reach top, and weight required to balance reduces, hence angle of contact increases to balance the reduced weight. Theta increases, cos theta decreases, surface tension force decreases. So only till that point angle of contact changes, theta increases, it will keep on increasing. Okay, vapor pressure PV is liquid gas. Okay, pressure, this is pressure measure. Even though liquid is stationary and liquid molecules are in continuous motion at molecular level, some of high energy velocity liquid molecules manage to escape surface of liquid and form vapor phase. This process is called evaporation. Evaporation is process is present at all temperature except absolute zero. Evaporation rate increases with molecular activity which increases temperature. As number of vapor molecules increase above vapor liquid surface, sum of vapor molecules combine together with form liquid. This process is called condensation. The condensation rate depends on on density of vapor molecules, number of vapor molecules per unit volume. At a given temperature, evaporation rate is constant, but condensation rate increases as number of vapor molecules increases above liquid surface. When evaporation rate is equal to condensation rate, then total number of molecules above liquid surface are constant. This condition is called saturation. Evaporation rate is equal to condensation rate. Okay, the pressure exerted by vapor molecules in saturation state is called saturation pressure or saturation pressure, temperature, or vapor pressure. Vapor pressure increases with increase in temperature as molecular activity increases. High volatile liquids have high vapor pressure compared to less volatile liquids. High volatile liquids have high vapor pressure compared to less volatile liquids. When minimum pressure falls below vapor pressure, liquid starts to boil and vapor bubbles are formed. This process is called cavitation. Cavitation is undesirable effects, has undesirable effects, hence it should be avoided. PV, okay. Chapter 1 fluid properties is done. Like